Hello, welcome Earthlings. This is Piero 314. I'm broadcasting worldwide from the great state of Maine via the WCAM broadcasting platform high in the midnight stratosphere. Welcome. This video is for Stephen Bro because he said that he liked going through these things, so I thought I would finish sort of what I had started. Now remember, okay, we have the measurables. Alright, these are time, space, and mass. Doesn't matter what you think these really are, if you have some idea or whatever. They're measurable is the point here. Now we have the variable we use, and we have the unit. The variable for time, we're going to use t. Space, we're going to use d for distance. Oh shit. Is it going to go away? No. And then M before I hit the button on my little tablet here. And M for mass. Right, the unit is seconds. For time. For space, we're going to use meters. A little bit confusing there. Please keep that straight, which M we're talking about. This one's the variable. And mass, we use kilograms usually. You can use any unit, but of course if you have 1 second, it's going to be a different number of minutes. So, alright, so we have that. So we want to remember that. Now, the thing about, I was explaining how you get, something like a kilogram meter. What does that mean? Well, it means a kilogram over a meter. You've taken it over a meter. So there's a meter and a kilogram together. That means a kilogram moved a meter. Right? That's how this stuff happens. But what if you have one of these variables squared? Well, distance squared is easy. You have feet and you have feet squared. It's like the difference between, a mile and a square mile. Between a couple hundred feet and an acre. Right? But when it's in time, or if it showed up in mass, it'd be very difficult for it to show up in mass, because where it shows up is when quantities change over time. Distance changes a lot over time. Mass in our equations is usually constant, but it doesn't have to be. You could have a mass that, say, was radiating and turning into energy, or even just a rocket burning mass, regular chemical fuel, and so the mass of the rocket, which includes the mass of the fuel, goes down as time goes, and you'd start to have those kinds of mass could end up squared. But I'm going to show with force what it means that time is squared, as I was talking about before. So first of all, let's go through this again. F equals ma. Okay, and what is a? Now, I'm going to not do all of the deltas here, because it's not important in this case, because we're going to take this as a moment in time. We can talk about that, but when you start doing all the deltas, delta D means d1 minus d0, so two different values. And if you take a delta in the delta, then you start to get a lot of d1, d2, d3, d4, all of these, and it starts to look complicated. And that'll matter when speeds are changing and things like that. But in this case, we can get the equation we're looking for. F equals ma. What does that mean? Well, F is isolated here. It means if I knew the mass and the acceleration, then I could calculate the force. But what was acceleration again? That's velocity over time. And velocity, of course, is distance over time. Right? So that means acceleration equals velocity, equals velocity, which is distance over time again, which equals d over t times 1 over t, which equals d over t squared, because when you multiply fractions, you just multiply the top and the bottom. Right? So this is the important part here. A equals d over t squared. Jesus. So that means that this equals m times a. A is d over t squared. Now, notice when we're multiplying the time, there's seconds in there, but they're going to add up into the unit of force when it's the force that's isolated. Well, let's say we had the force and the mass and the time, and we didn't have the distance. In other words, if we had a rocket pusher, it's a rocket pusher here. This has a little pusher up here, and it pushes your little thing with your window in it. It just pushes it. Then when it stops, it turns around, and you just go flying through space. And the rocket has a constant force that applies, F. Right? And, we know what the time is because we want to know the number when it's been, 1,000 seconds. Well, how would that work? D is over here. Well, we have to isolate D. Now, this is one of the easiest things that always seem to confuse other people about how you move variables from one side to the other. Remember, this equation is like a teeter-totter, right? And it's perfectly balanced right now. How do I keep it perfectly balanced? How can I move the m over to this side and get a alone? And the answer is you can add, subtract, multiply, or divide either side as long as you do the same thing to the other side. Right? So 2f equals 2m d over t squared. Right, I can just multiply both sides by 2. That'd be fine. But why would I want to do that? Well, I wouldn't. But if I want to get d alone, I can multiply by t squared on this side. And I have to do that on this side too. These cancel out. Boom. It's moved over there. Okay, now I still have md on this side. And f, I'll put the t squared second, on that side. Because, of course, I hope everybody remembers when you have multiply numbers, you can multiply them in either order. Now I want to get the m over there. Well, I can divide this side by m and this side by m, and then those cancel out, and I have d on this side, and f times t squared over m on that side. And we have the isolated variable. We like to put it on that side because it looks nicer to us. Now, if I have the mass, right, the mass of this thing that's getting pushed, and I have the force, so this thing has a mass, right? Let's say it's 1,000 kilograms. And the force, well, it doesn't matter. I'm not going to make them numbers for all of them. And then the time we want is 1,000 seconds. Well, now I could plug those all. I guess I have to make a number. Let's say that this is, oops. I hate when that happens. Okay, this equals, I don't know, 500 joules. All right. And we want to do this at time equals let's just say 10 seconds. Now let's say 5 seconds, so we don't just have multiple of thousands. Okay, now as you can see, the number 5, or 5 seconds rather, is going to get squared, and the time is going to get squared, but there's a time squared on the bottom of a joule already, right? Remember, the joule unit is kilogram meters squared over time squared, right? So that time squared of the t here is going to get canceled out unit-wise. And what the square is really going into is the d. It's saying that if you have twice as much time, the distance is actually going to be 4 times further. Why? Because it's falling faster and faster. So if you have 8 times, 8 seconds, you're going to have to square that. It's going to be 64 times faster than just after 1 second. So it's the distance that is seeing the effect of the squared. Right? It's the distance that the more the time, the faster and faster the d is going, so the effect of time is compounded. Every second gives it more and more. So anyway, if somebody for some reason wanted that all put in there, we'd say d equals 500. I'll write the unit out. 500 kilogram meters squared per second squared. Just running out of space here. What should I do? Right over here. A different color. Okay, so we have distance. Oh yeah, I like that one thicker. So we have no, that's too thick. Let's go back to black. Alright, so the point is that we have distance equals 500 joules. Joules is kilogram meters squared per second squared. That's over the m. So that's the force. We're going to times 5 seconds squared, right? And then the mass, I said, was 1,000 kilograms. All right. Oh, I'm sorry. I know what I did wrong. I was looking at this. This is not. This is not joules. Sorry. Oh, this is newtons. Okay. Made a mistake. So that's newtons, and newtons isn't meters squared, because see, the units weren't working out. Okay, so it's kilogram meters. because a Newton, the unit of a Newton is a kilogram meters per second squared. Okay. Because the units, see, you could check the units to see if you're making a mistake. Okay, so this is on top, and that's on the bottom. So let's deal with the top. First of all, this is going to be, see, what's the easiest way for you guys? I mean, basically, there's some interesting things going on. I want to multiply this top out first, so we have 500 kilogram meters per second squared times 25 seconds squared, because 5 seconds squared is 25 seconds squared. And this is all over 1,000 kilograms. These seconds divided by that seconds cancel out because that's 1. And that leaves us with D equals 500 kilogram meters over 1,000 kilograms. Kilogram divided by kilogram is 1. So that is 500 meters over 1,000, which equals 0.5 meters. So it wouldn't go very far, because that's not a very strong force. Now you can see if I put in 50 seconds, well then it'd go 25,000 seconds squared, and that'd be a lot more. Right? Just 4 times more, but it'd be a lot more than 4 times 0.5 meters, because it's going faster and faster and faster. So that's the purpose of having this, not the purpose, but why you see these relationships. Because in something like force, this is like if you apply a force, how fast are things going to go? Well, the bigger the force, the faster it goes. Since it keeps going faster and faster, you have these compounded elements, and in this case, it's time. Doesn't have to be time. There's other ways for that compounding factor. As I said, it could even happen with mass if you're losing mass somehow over time, or gaining mass, say, from an accrual process. All right, sorry about the mix-up between joules and newtons, but it did show that I knew when the units weren't going to work out that I had made a mistake, because the unit analysis is like the formula that you can look at without the numbers and just seeing how the units work, because all of these units have a meaning. When you take, distance and you divide it by time and call that velocity, you're making a relationship between distance and time. And it's different than distance times time. Distance times time is like the distance and you're multiplying it by a time because it goes over that time, whereas distance divided by time is actually, even though we call it a fraction, it's like over it, it's really per time. So it's a distance per time as opposed to a distance that is taking place for a time. So when all of these relationships work out, you're going to end up seeing these compound relationships where, for example, here, the longer you apply a force, the faster and faster the velocity, and therefore the distance gets bigger in proportion to time squared. And that's why you see things like time squared. And thank you, Stephen Bro, for asking. I appreciate that. Made it more fun to go ahead and do it. All right, I appreciate it, because I'm trying to make this show a regular show, because it obviously is a show, and nobody would deny that. What does MD mean? Ravel to expand asks. Mass times distance. You must have missed the beginning, Ravel. That's okay. You can watch the VOD. It's this thing here. See, basically, all of this physics, classical, all physics, even the non-classical kind, it's always in terms of these elements: time, space, and mass. And we are using the variables t for time, d for space, because that's distance, and m for mass. Now, one problem here is, look, m, this is a meter. M for meter, this is the units. The measurable, so these are the measurable things. I guess I could try to write better. And so this is the variable, and this this is the unit. Now you can use all different kinds of units, but we use seconds, so those are where the S goes for instead of space, and then kilogram. Of course, these could be other units, but so m times d is mass times distance, and it comes up because this is force, or in momentum is mv, p momentum equals mv, v is d over t, right? So momentum is m d over t. So this is the whole point of talking about this, is that that's all classical physics is. And even the modern physics, the point is the philosophy, the natural philosophy behind it is that anything in the universe that exists is measurable, and these are the only three things that are measurable, right? So if you ever measure love, it'd be by measuring the effect on time, space, and mass. And you could think of that neurologically and all that. That's where it's really happening. Or you could say if love is real, you believe it's real, and it's a behavior. Behavior is people, objects moving through space and time, and their mass bumps into things. That's how you pick stuff up. So the interactions between those three quantities, the nice thing, because they are quantifiable, is you can relate them with mathematics. And when you multiply, a distance by a time, that has a physical meaning, right? Just like, hey, I picked up an object and I threw it in the water. That has a physical meaning. Hey, I put my keys down somewhere and I can't find them. That has a physical meaning. Well, when you multiply mass times space, or divide, mass by time, right? Like mass by time. Why would you have mass divided by time? Well, if you have a pipe and it's out of the pipe is coming grain, there's a speed of that. There's the mass of the grain per unit of time, right? There's a bushel per minute. And actually, any mixture of these quantities has a meaning like that, but it can get quite esoteric. And so basically what I'm saying here is that we have with acceleration and velocity the least esoteric. We're just talking about things are moving, okay? That's change in distance over time, so that's fairly straightforward, right? And then we know you could speed up and slow down, so it's even intuitive to our body, this concept of acceleration, right? You can also have the change of acceleration over time, which actually does have a name, if I recall correctly, jerk. And that can be important in aeronautics and stuff, but mostly we don't think about it, but there probably is a physical, jerk's probably a good, it's like more than acceleration, smooth acceleration, so, because the acceleration is changing. And you can have the change of jerk over time, and those are all the further derivatives of just distance. So I think you get a good understanding with knowing what distance is, and then you have change of distance over time, and then you can have the change of the velocity over time. Boom, and right there we're up to Newton point almost. Right there we have all the measurables and we're relating them, except for what about, mass. So when you add mass to the acceleration, so you have a mass and you accelerate it, so you're multiplying them because it's the mass over the acceleration, well, that's equal to the force. Right? And so with force, you finally have all three of the quantities together. That's why it's so beautiful as a philosophy. It came from natural philosophy. Now all the mathematics and technology and other things you can do, that's all great too, really. Obviously you can make weapons and you can make it terrible too. But in terms of a natural philosophy, it's amazing how well it works. That really in just these steps, distance, velocity, acceleration, that's common sense. Something having a weight, that's common sense. You multiply those two, mass and acceleration, boom. Acceleration has the velocity concept. It's really all just the distance concept over time. Then, oh yeah, you'd really hate it with the jerk, because then you might have t cubed and all kinds of stuff like that. But stopping at force, you have m in with that. You've got all three of them. They're all connected. And then energy and momentum are fascinating as the next layer. And after that, there's a lot of complicated math problems you can do for specific cases, but it's funny. All thermodynamics, and so that means engines and everything like that, and all forms of energy and motion, energy especially, share the same units, right? Which is the joule. And so it connects like all of the kinds of physics. I mean, all quantum mechanics is doing is has conservation of energy. It's the same kind of energy with the same kind of units. It's just, on a nuclear level and different physical effects, right? Because, space, time, and mass don't say there is or isn't a photon. It just says that if there is a photon, you'll know because we'll be able to measure it in terms of space, time, and mass. Right? And quantum mechanics is the same thing. So that part of the natural philosophy of this physics, is solid. There is no controversy. They all hook together that way. So after force, you have momentum and energy. Momentum is when you take a force and you apply it for a certain time. Then you'll get a momentum because it's force times time. And energy is when you take a certain force and you apply it over a certain distance. Then you get energy. So, and in those layers, just the simple, it's like, depends on how you want to count the layers, but, it's distance, velocity, acceleration. But to me, that's one layer, because so far that's all distance and time. And then you have mass, and that's the force layer. And after that, you have mass over distance, mass for a distance and mass for a time. And that's, if you understand those concepts, then that is classical physics. It overlaps with thermodynamics, which, in the mathematics of combustion and stuff. But that's also where classical physics started to fail, and we needed other explanations for how energy is transferred and works, and we needed statistical approaches, and we needed more advanced calculus, because things aren't just perfectly round spheres; they're lumpy and in different shapes and whatnot, and because there's atomic physics, right? But they still use all the same, force and mass, and that stuff is all still the same. It's just generated in a different way, and you can still demand to be able to measure the effect of these things that are considered physical in terms of time, space, and mass.